Hello, my name is Jillian Lee. Today I will be guiding you through an experiment that is based on some crucial physics principles, specifically Newton's second law. The first part of this experiment is to video an object moving at constant speed in a single direction, and then to analyze the video using Tracker to determine an object's position and time. This data will be then used to make a computational model that describes my observations based on physics principles. The computational model will then be used to compare to the experimental model by plotting both the observed position versus time and the predicted position versus time on the same graph. For this experiment, a tennis ball of known diameter and weight was rolled down a level surface, an ironing board, in one direction. The motion was then captured on camera using a cell phone. The video was then uploaded to Tracker software to collect data. The video was checked for a constant frame rate, in my case 30 FPS, which indicates that 0.033 seconds are between each data point. The diameter of the tennis ball was used to calibrate the software. The axes were set based on the tennis ball's initial position. I chose to have the ball rolling from the initial center of origin down the negative x-axis. It's important to note that the axis set is not significant. If I chose to have the ball rolling from the positive x or negative y axis, it wouldn't have really changed the data collected, except for maybe a positive or negative sign. The ball is still experiencing the same force and movement, independent of what the axes are set to. The frames in which the ball appeared to be moving at a constant velocity were chosen to be analyzed, in this case from frames 17 to 39. Tracker gave specific information about the ball's position, motion, and time data, which allowed for calculation of the ball's initial velocity. It's based on the formula V initial equals delta R over delta T, where delta R is change in position and delta T is change in time. Plugging the data from Tracker into the equation gives us an initial velocity of negative 1.235 meters per second. The computational model created in Python allows one to predict the final velocity and position of the object by manipulating Newton's second law. Given initial position and velocity, the future position and velocity can be predicted using these two equations here, where R2 equals R1 plus V1 times delta T, and then V2 equals V1 plus F net over mass times delta T. In Python, this calculation is carried out in the while loop. Inside this loop, there are commands that tell the computer how to increment the velocity and the position according to the equations for predicting velocity and position. In my program, the lines that implement these vector equations look like this. Since information was recorded when the ball was moving at a constant velocity, we assume that no net forces are acting upon it. The results of the computational model and the experimental model are compared by plotting both the observed position versus time and the predicted. The computational model and the experimental model seem pretty close to each other, but we can see the computational model is not a complete, accurate representation of the experimental model. So why do the experimental and computational model differ from each other? This experiment has many sources of error. The computational model's assumption of zero net force and constant velocity is one of them. In a perfect world, as in the computational model, there is no net force, but on an uneven warped surface like an ironing board that was used for the surface in this experiment, the velocity will not be constant. Friction will also lower it as well. In the experimental model, there are many pushes and pulls and forces coming from uncontrolled aspects that are added together to give an almost zero net force. It would be possible to say how many pushes and pulls are added together by taking more frequent measurements. However, the accuracy of this would be very difficult to achieve because you would have to take very small frequent measurements. Human error also plays a role in this experiment. To create our initial measurements, in Tracker we recorded the position, so any mistakes in measuring here would have been multiplied when the velocity was calculated, so human error could have been prevalent here as well.